Welcome back. Today we're going to talk about lesson 9.3 day 1, the significance test for means. Now, like the significance test for proportions, the same thing goes for means. We're going to be looking at some conditions that make it possible for us to actually run these tests and the mechanics of running these tests. So let's go ahead and get started. Important ideas here. The first one is we've got to outline our conditions. And our conditions are going to look a lot like what we've seen in the past. First of all, it's got to be random. So it's going to say something like a random sample was taken, or we have a simple random sample taken. And so that's going to be our first of the conditions that need to be met. Then it's going to need to be normal. This can mean one of three things. The first thing that it can mean is it could mean that the population is normal. Right? And our sample is going to mirror the characteristics of our population. Or it could mean that our n is greater than or equal to 30, which would allow us to use the central limit theorem to say that the distribution is normal. Or if neither of those conditions are met, we can look at it and say, all right, what does my graph tell me? And if the graph has no strong skew, or outliers, no strong skew or outliers, we can say that it is normal and that condition will be met. The last thing that we're going to be looking at is that 10% condition met? So our 10% condition says, is our number less than a tenth of our total population value? So those are the three conditions that need to be met before we can actually run these tests. Now, the mechanics of the test are going to look a lot like what we did for proportions. So when we look at this actual test, what we're going to be doing is we're going to be finding a test statistic. Okay, and our test statistic is going to be equal to t, whereas before, we had p. So in this case, it's going to be t, and it's going to be our sample mean minus our population mean over our standard deviation of x divided by the square root of n. And important to put that in parentheses, but you'll notice on the bottom, that's the standard deviation for a mean. That's that standard formula that we have on our formula sheet. So when we look at our graph, what we're looking at is finding t, and then we have a degrees of freedom situation, right? So there's a couple of different ways we could actually find this value here. Our p-value, the probability of this happening, could happen in a couple of different ways. The first one, we could use table B. And that's where we have the degrees of freedom and the confidence level, right? So with df and tail probability. Or we could use our calculator to do TCDF, and that's going to be lower and then upper, and then putting in our degrees of freedom at the end of that parentheses there. So that's how this works, right? So we have not only the conditions that in red here, then the formula for the test statistic, and then how we find the p-value to actually interpret this. So let's do a little example here under this check your understanding. So the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen at a level at 30 randomly chosen locations along a stream. Here are the results in milligrams per liter. X bar is equal to 4.77, and the standard deviation is 0.939. An average dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Do the data provide convincing evidence at the alpha level of 0.05 significance level that aquatic life in this stream is at risk? So, start out by stating everything that's going on here. And so, this is the same process that we've gone through. So, our parameter is going to be the mean, which is the true mean of dissolved oxygen level. Okay, that's what our parameter is. And our hypotheses, check back to what we've got going on here. And so what we're looking at is this situation right here. An average dissolved oxygen level of 5 milligrams per liter puts aquatic life at risk. So our hypotheses, our null hypothesis, H sub 0, is going to be that our mean is equal to 5 milligrams, and our alternative is going to be that it is less than 5, because that 5 puts it at risk, so we're trying to figure out that if it's below. So here we go. All right. Our statistic that we're actually looking at is what they said was our X bar. And so after they ran this actual experiment, they found that X bar was equal to 4.77. What we're trying to figure out is if we put a 5% significance level on that, is that enough to suspect, because it is below, that it could just happen by chance, or is there a reason to investigate the claim of 5 milligrams per liter? So our alpha level is 0.05. And so what's the name of our procedure here? We're still doing a one sample test, but we're doing a one sample t-test. For mean. And we have to check our conditions. So let's see. When we look back at our problem here, what we have is we have randomly chosen locations. So that's going to satisfy our random. Yes, because it says randomly chosen. In quotes. Does it meet our 10% condition? So let's look. Is it 10%? Is that less than 1/10 of all locations in a river? I would think so. So 30 is less than 10% of all locations. And is it normal? So let's look back here. Maybe you already know the answer to this question. Let's see. Level of dissolved oxygen, researcher measures, da 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 da. Well, look at our sample size. So right here, right there, 30. So we have our condition met here because n is equal to 30, and 30 is greater than or equal to 30. So CLT for means, this is normal. This is good because now we can use all of our functions. So what are we going to do? We are going to do this one sample test. So let's see what we've got here. Okay. General. We are going to do this test. And it's going to look like us doing a test statistic. Our formula for that is X bar minus our mean over Sx divided by our square root of n. And so, well, that's not our general, that's actually our specific. So these kind of together, I got ahead of myself, but the general would be test stat is equal to stat minus null over, over standard deviation. So here's the formula we're actually going to do here. And we actually have a lot of these values, which is kind of nice. So let's go ahead and actually do it. Drawing our picture, what we're finding is we are looking at, here's our normal curve. We determined that it was normal. We have a value here of 4.77, and we're finding what's the probability that it would be 4.77 or lower. And our t-value is based on 29 degrees of freedom. So when we actually do this work, we're going to zoom in here and do the work. We have 4.77 minus 5 over standard deviation was given as 0.939 divided by the square root of 30. And I'm going to make sure to put that in parentheses because I've got that denominator there. What I find is that I have a t-score of minus 1.33. Now, couple of things. That gives me my test statistic. So what is my p-value? So I am actually going to figure out based on, I'm going to use my calculator, and I'm going to do TCDF. And what I'm going to do is I'm going to say I want, now notice my picture here. This is where this comes in handy, right? So I want 4.77 or below. Well, 4.77 is actually t equals negative 1.33. So I'm going to do negative 1,000 because that's below. And I'm going to go all the way up to negative 1.33, and my degrees of freedom are going to be 29. When I plug this into my calculator, what I get is 0.097. So that's what I'm comparing to my alpha level, because the probability of getting this negative 1.33, or this test statistic of negative 1.33, is actually 0.097. Let's look at the full picture here. So right here, let's see. So right over here, I did my work to find that test statistic. Just listed it here. I did my TCDF to find out what the probability of that was. Well, now I need to write my conclusion. So I'm comparing that to that 0.05. And so I have to make a couple of assumptions here, because what we just did was we assumed that the mean was going to be 5. And so assuming a mean DO level of 5 milligrams per liter. And I know that because that was what my null hypothesis was, right? So assuming that that is true, there is a 0.097 probability ability, which I should have. T, can't spell. Probability of getting a sample mean of 4.77 purely by chance. Right? Because that's what I found that probability to be based on my test statistic. So how do I interpret that? So this provides weak evidence against the null. So that's weak evidence against the null because it's above our alpha level. We don't have enough evidence to say, maybe we should investigate that. And we fail to reject the null. That's kind of our piece right there, right? That's what we want to do. We want to know if we are rejecting the null or supporting the null. So if we assume that 5 milligrams per liter, then that was what we based all of our test statistic work on. Found that test statistic to be negative 1.33. The probability of getting that was a 0.097. When we compare that to an alpha level of 0.05, we find that it's actually not convincing evidence against the null, so we can't reject the null based on that. So that's the basics of the mechanics. And so what we're going to talk about now is the power of a test. So let's talk about power. So we've pretty much concerned ourselves a lot with the null hypothesis and assuming that it's true and finding this test statistic based on it. But now we're going to look at what's the power of the alternate hypothesis? What's the power behind it? And how do we put a number on it for how probable it is? And so here's what the power interpretation is. Important idea from this one. I'm going to grab green here. Power interpretation. So here's what power interpretation means. So if we assume, assuming the true mean is blank. So whatever they give us as that number. There is a blank probability of finding convincing evidence for the alternative blank. Okay, so what does this actually mean? This is another fill in the blank. I get a lot of these in statistics, right? But right here goes your power number. So the power number is the probability of the alternative actually happening. So that's where we put the power in. And so a chart that can help us here, because really what we're actually doing is we're working with type 1 and type 2 errors, but also accepting and rejecting the null and the alternative all at the same time. And so let's look at a little chart that can help us sum all this up. So there's a two-way table here. So here's truth up here. So two things could happen. And I'm going to draw this out like this. So one of the things that could happen is H sub 0 could be true, right? So the null hypothesis could be true. Don't make it out to be a bad guy. It could be true. Or the other alternative is H sub A is true. So those are our two alternatives there. On the side over here are the two outcomes that could happen. And we don't talk about the alternative hypothesis. We're talking about the null hypothesis. So one of the things that could happen is we could reject the null, or we could fail to reject the null. So what goes in the four boxes? If the null is true and we reject it, that's actually an error. So that's a type 1 error. So this can kind of help, right? So a type 1 error would be if the null is actually true and we reject it. So let's say somebody says, oh, 50% of people do this. And you say, no, that's not true. But it actually is. That's a type 1 error. Well, if the alternative hypothesis is true and we reject the null, that's actually good. That's what we want. It's good to reject the null if the alternative is true. So if somebody says 50% of people watch this show, and I say, no, I don't think that's true, I think it's less, and we find that it's less, and I say, your hypothesis is false, that's good, that's what we want. On the other hand, if the null is true, and we fail to reject it, that is good, right? So 50% of people watch this show, and I say, yeah, I think that's true. And it is, that's good. But if the alternative is true, and we fail to reject the null, meaning we'd say, well, no, the claim isn't true, this would be a type 2 error. And so, probabilities here. Probability of a type 1 is our alpha level. Because that's the level that we're drawing that line and saying below this level comes an error, right? So that would be we had that 5% threshold. Below that would be where we cut it off so we could miss. Of a type 2, it would be 1 minus the power. Okay, 1 minus the power. So let's check our understanding. So this is going to be a basic problem that involves power. We're going to make some interpretations on it. So here's the whole set of notes up there. Can a 6-month exercise program increase the total body bone mineral content of young women? A team of researchers is planning a study to examine this question. The researchers would like to perform the test of H sub 0 where the mean is 0. So that would mean the average was 0. And then the alternative was greater than 0, where mu is the true mean percentage in change of during the exercise program. So a change of 0 would mean, so a mean change of 0 would mean no change, and then greater than 0 would mean there is a change. So the power of the test to detect the mean increase in the total bone body mineral content of 1% using an alpha level of 0.05 and n equals 25 subjects is 0.80. Interpret this value. So the power is 0.80. So this is that fill in the blank up here that we had. So assuming the true mean is what is stated, %1 change. So assuming the true mean is 1% change, there's an 80% chance probability that the test gives convincing evidence for the alternative. And you should tell what the alternative is. And that would be that the mean is greater than 0. Okay, so the power tells us the probability of the alternative being true. So find the probability of a type 1 error. So our type 1 error is equal to alpha, which is equal to 0.05. And our type 2 error would be 1 minus the power, which would be equal to 1 minus 0.8, which is 0.20. Okay? So let's look at the implications of this. So determine whether each of the following changes would decrease or increase the power of the test. Explain your answer. So if we use an alpha level of 0.01 instead of 0.05, would this increase or decrease the power of the test? So if we lower our probability of a type 1 error, think about what happens. We lower this alpha level. It makes finding convincing evidence to reject the null more difficult. So it would actually decrease the power because it makes it harder to find evidence that would go against the null. Okay, so think about that for a second. You lower that alpha level. Now all of a sudden you've got to be in that 0.09, so 0.009 probability range, so below 1% of a chance happening. So it's very difficult to find a convincing situation for having evidence against the null. What if we used n equals 100 instead of n equals 25? So it would be an increase because increasing sample size increases power. Because sample size up increases power. Okay, so that's the basics of what we've been talking about here. So to review, power is the probability of the alternative being true, and so that affects what type 2, like our probability of our type 2 error. We also reviewed that a type 1 error has a probability of equal to the alpha level. So changing that alpha level changes what type of or how easy it would be to find convincing evidence against the null, which would then affect the power because the null and the alternative are tied together in their probabilities, but also because they both can't be true at the same time. They're alternative ideas to one another. And so if the alpha level goes down, then the convincing evidence against the null goes down, which decreases the power of the test, which means it decreases the likelihood that the alternative is true. So that's what we're talking about in this one. So thanks for watching, guys, and we'll see you next time.